Light travels about 5,878,000,000,000 miles in a single year. 5,878,000,000,000 miles. That number is almost impossible to hold inside the human mind. But we are going to try, because today we are asking the question almost nobody asks out loud. If we pointed our fastest spacecraft in one direction and let it fly, how long would it take us to cross just one light year? Not to the edge of the galaxy, not to another star system, just one light year. What we found changes everything you think you know about distance, time, and what we are actually capable of. We are going to travel through frozen clouds at the edge of our star system, push engines that run on the power of stars, and face the strange reality that time itself bends when you move fast enough. If you want more of this, subscribe and hit like. It genuinely helps. Take a breath. The journey starts now. Here is a number. 5,878,000,000,000 miles. That is one light year. The distance light covers in 365 days, moving at about 186,000 miles every single second. Most people hear that and nod. Then they move on. But if you actually try to hold that number in your mind, something strange happens. It stops feeling like a number. It starts feeling like a wall. So let us try to make it real. Imagine you are driving a car at 60 miles per hour. No stops, no sleep, just driving. To travel one light year at that speed, you would need roughly 113 million years. The dinosaurs went extinct about 66 million years ago. You would need nearly twice that time just to cover one light year in a car. Now try a plane. A commercial jet flies at roughly 500 miles per hour. Point it toward that 1 light year mark and let it go. You would arrive in about 1,300,000 years. Anatomically, modern humans have only existed for around 300,000 years. The math is not just big, it is disorienting. Even if you tried to walk it, assuming a healthy pace of 3 miles per hour, it would take over 2 trillion years. The universe itself is only about 13.8 billion years old. You could walk for more than 140 times the age of everything that exists and still not finish. Light years are not just a unit of distance. They are a unit of impossibility, at least with anything we currently have. And here is what makes this stranger still. 1 light year is not even close to the nearest star. The closest star system to ours, Alpha Centauri, sits about 4.2 light years away. The center of our galaxy is around 26,000 light years from where you are standing right now. The observable universe stretches roughly 93 billion light years in every direction. 1 light year is the smallest meaningful unit of interstellar scale. It is basically the first step out the front door, and that step alone would take everything we have. But here is what keeps scientists and engineers up at night. Speed is not fixed. Humans have been getting faster, slowly, steadily, without stopping, from walking to horses, to steam engines, to aircraft, to rockets. Each leap forward opened distances that were previously thought unreachable. So the real question is not just how far 1 light year is. The real question is how fast we can go, because the answer to that second question changes everything about the first. And when you learn what our fastest spacecraft has actually achieved and compare it to what would be needed, the numbers get fascinating in a way that is almost uncomfortable. Something is waiting on the other side of that discomfort, and it is stranger than the distance itself. Light does not ease into its speed. It is already at full velocity the moment it exists, 186,000 miles per second. That is not a speed limit in the casual sense. According to everything we understand about physics, it is the absolute ceiling of the universe. Nothing with mass can reach it. The closer you get, the more energy you need, and the math curves toward infinity before you ever touch that number. To put the speed of light into a scale that actually registers, in the time it takes you to blink, light has already traveled roughly 11,000 miles. A single blink. 11,000 miles. Light crosses the entire width of the United States in about 1/100th of a second. It circles the entire Earth about 7.5 times per second. It reaches the Moon in just over 1 second. Now, compare that to us. The fastest crewed spacecraft ever launched was Apollo 10 in 1969. It hit a top speed of about 24,791 miles per hour during its return from the Moon. That felt extraordinary at the time. Humans were genuinely moving faster than any person in history. But 24,000 miles per hour is about 0.004% of the speed of light, not 4%. 0.004%. Even our uncrewed probes, which do not need to carry life support or return home, top out in the range of 35,000 to 40,000 miles per hour relative to our star. Still, a tiny fraction of light speed. Physics puts a hard wall in front of us. The faster something with mass moves, the heavier it effectively becomes. Think of it this way. The energy needed to keep accelerating grows with every mile per hour gained. And as you approach light speed, that requirement climbs toward a value no power source in existence could provide. Einstein described this in 1905, and every experiment since has confirmed it. The speed of light is not just fast, it is structurally unreachable for anything made of matter. So, if we cannot reach light speed, the question becomes, how close can we actually get? Even 1% of light speed would be a revolution. Even a fraction of 1%, sustained over years, would change everything about what we can reach. But generating that kind of sustained acceleration requires an engine unlike anything flying today. We have concepts. Some of them are surprisingly credible. But before we get there, we need to understand what we have actually built, what it has already achieved, and how far it has traveled since we let it go. Because right now, there is a human-made object heading toward interstellar space. It has been flying for over 4 decades, and it has barely made a dent. On September 5th, 1977, a rocket lifted off from Cape Canaveral, carrying a spacecraft roughly the size of a small car. Its name was Voyager 1. Nobody alive at the time fully understood what they were watching. This was not just another probe. It was going to become the farthest traveling human-made object in history, a title it still holds today. Voyager 1 used a rare planetary alignment, one that only occurs every 176 years, to slingshot itself past Jupiter, then Saturn, gaining speed from each planet's gravity like a stone flung from a sling. This technique, called a gravity assist, allowed it to reach speeds no rocket alone could generate. Today, Voyager 1 is moving at roughly 38,000 miles per hour relative to our star. It has been flying for over 47 years. In that time, it has traveled about 15 billion miles. That sounds enormous, and in human terms, it is. 15 billion miles is so far that signals from Voyager, traveling at the speed of light, take over 22 hours to reach us. But 1 light year is 5,878 billion miles. Voyager 1 has covered roughly 0.0002 light years. It would take approximately 73,000 years to cross 1 full light year at its current speed. 73,000 years. When Voyager 1 was launched, the ancient Egyptians were still 4,000 years away from building the pyramids. 73,000 years before its launch, modern humans were still painting cave walls and hunting with stone tools. And yet, Voyager 1 is the best we have ever done. Parker Solar Probe, launched in 2018, has achieved the highest speeds of any spacecraft by diving close to our star and using its gravity. During its closest approaches, it has reached nearly 430,000 miles per hour. That is genuinely remarkable, but even at that speed, 1 light year would take roughly 15,000 years. These numbers reveal something important. Our current propulsion technology, rockets burning chemical fuel, is essentially the same category of engine that launched the first satellites. We have optimized it, refined it, made it more efficient, but we have not changed what it fundamentally is. Chemical rockets are controlled explosions. And controlled explosions, no matter how powerful, are nowhere near enough for the scale of interstellar space. There is a kind of strange beauty in Voyager 1, though, a machine built by human hands, powered now by the decay of radioactive material, drifting through the dark between the stars, still sending signals, still being heard. It will outlast every person alive today. It will outlast most of what we have built, and it has barely left the neighborhood. What would it take to actually cross that distance in a human lifetime? The answer requires throwing out almost everything we know about how spacecraft are built. Let us do the math together, because the numbers are where the reality actually hits. Take Voyager 1, 38,000 miles per hour. 1 light year equals 5,878,000,000,000 miles. Divide that distance by that speed, convert the hours into years, and you get roughly 17,500 years. Some estimates put it closer to 73,000, depending on future deceleration. Either way, we are talking about a span of time longer than recorded human history. Now take Parker Solar Probe at its peak speed of 430,000 miles per hour. That gives you something closer to 15,000 years for 1 light year. Still, 15,000 years. What if we could somehow build a spacecraft that moved at 1% of the speed of light? That would be about 6,700,000 miles per hour. Vastly beyond anything we have achieved. But at that speed, 1 light year would take 100 years. A human lifetime, barely. 10% of light speed, 10 years to cross 1 light year, that starts to feel almost manageable. But here is the catch. Getting to even 1% of light speed requires energy on a scale that makes current rocket technology look like a candle next to a nuclear reactor. To put it in terms you can feel, the kinetic energy of a spacecraft the size of Voyager 1 moving at 1% of light speed would be roughly equivalent to the energy released by several thousand nuclear weapons detonating simultaneously. You have to pour that energy into the spacecraft somehow, in a controlled and sustained way, across the entire duration of acceleration. No chemical rocket can do that, not even close. And there is another problem almost nobody thinks about: stopping. If you somehow accelerate to 1% of light speed, you need just as much energy to slow down at the other end. Unless you want to pass your destination at millions of miles per hour and never actually arrive. The journey to 1 light year is really 2 journeys. One to get there, one to stop. Double the energy, double the engineering, double the time. This is why interstellar travel is not just a distance problem. It is an energy problem, a physics problem, and a materials problem, all stacked on top of each other. And underneath all of those technical problems is one more that does not get enough attention. Even if we solved every engineering challenge tomorrow, even if we had the engine and the fuel and the structure, there is still the matter of who is on board and what happens to them over the course of a journey that could last centuries. Because the human body was not built for this, not even slightly. The human body is a product of Earth. Every system inside you, your heart, your bones, your immune system, your sense of balance, evolved over millions of years in one specific environment. Gravity pulling at 9.8 meters per second squared, a 24-hour day, oxygen at a precise concentration, sunlight cycling on a rhythm your cells have memorized. Remove any one of those conditions and the body begins to fail. Remove all of them and the deterioration accelerates in ways that still surprise researchers. We know this because of the International Space Station. Astronauts who spend 6 months in orbit return with measurable bone density loss, weakened muscles, compromised immune systems, and in some cases, shifts in the structure of their eyes caused by fluid pressure. changes in microgravity, 6 months. And these are the healthiest, most carefully monitored humans on Earth. A journey to 1 light year, even at speeds we cannot yet achieve, would take decades, more likely centuries. The body would not survive that journey in any recognizable form without extraordinary intervention. Bone loss in microgravity occurs at roughly 1 to 2% per month. Without countermeasures, a crew member on a multi-decade journey would lose so much bone density that fractures could occur from minor movement. The skeleton would essentially hollow out. Muscle mass follows a similar pattern. Without the resistance of gravity, muscles have no reason to maintain their size. The heart, which is itself a muscle, shrinks. Cardiovascular endurance collapses. Radiation is perhaps the most serious concern. On Earth, our magnetic field and atmosphere deflect the majority of cosmic radiation. In deep space, there is nothing between you and the full spectrum of high-energy particles streaming from dying stars, colliding galaxies, and sources we still do not fully understand. Long-term exposure dramatically increases cancer risk and has been shown to cause measurable cognitive decline in animal studies. The NASA Twin Study, which followed astronaut Scott Kelly after a year on the space station while his identical twin Mark stayed on Earth, showed changes in gene expression, gut bacteria, and cognitive performance. Some changes reversed after Scott returned. Others did not. 1 year produced those results. Imagine decades. And none of this accounts for the psychological dimension, which may be the most underestimated danger of all. Isolation does something specific and measurable to the human mind. The further you travel from Earth, the longer communication delays stretch. At 1 light year out, a message home would take 1 year to arrive and another year for any reply. The crew would be, in every practical sense, completely alone. No rescue, no reinforcements, no one coming. The body has limits, but the mind has different ones, and they tend to break first. Scientists have been quietly working on ways around both. Some of the ideas are serious. Some are closer to science fiction than anyone wants to admit. One of the most discussed is the possibility of putting the crew to sleep for the journey. Bears do it. Ground squirrels do it. Certain primates in Madagascar do it. They slow their bodies to a crawl, drop their temperature, halt digestion, reduce their heartbeat to just a few beats per minute, and wait. Months pass. They barely age. Hibernation is real. And for decades, researchers have asked whether it could be extended to humans. The idea is simple in theory. If you could put a crew into a state of suspended metabolism during a long interstellar journey, they would not age at the normal rate. They would not need food at the normal rate. They would not go psychologically unstable from isolation, because they would not be conscious to experience it. A crew that enters sleep shortly after launch could, in principle, wake up near their destination decades later, having experienced very little of the journey. But humans are not bears, and the gap between those two facts is enormous. Human hibernation does not naturally exist. Our core temperature cannot safely drop below around 95 degrees Fahrenheit without triggering dangerous cardiac events. Our cells are not adapted to survive the metabolic slowdown that hibernating animals handle with ease. There is one exception that gives researchers genuine hope: therapeutic hypothermia. In hospitals, doctors sometimes deliberately lower a patient's body temperature after cardiac arrest or brain injury to reduce damage. Patients can be kept in a cooled, unconscious state for days. Their metabolism slows, their oxygen needs drop, and in many cases, they recover. This works for short periods, measured in days. Scaling it to years is a problem that has not been solved, and some researchers believe it may require a fundamentally different approach. SpaceWorks, a company that has received funding from NASA, has proposed a concept called torpor-inducing stasis. The idea is to keep crew members in a rotating cycle, perhaps 2 weeks asleep and a few days awake, managed through a combination of cooling, nutrients delivered intravenously, and careful monitoring. This falls short of full hibernation, yet it would dramatically reduce resources needed and limit the psychological strain of long-duration isolation. The biology remains the hard part. Prolonged unconsciousness without brain stimulation carries its own risks. Muscles still atrophy. Bones still lose density, although the rate appears to slow in cooled states. And no one has tested anything close to this in humans over the timescales an interstellar journey would require. Some researchers argue the real answer is eliminating the crew entirely, sending artificial intelligence and robotics to do what fragile biological bodies cannot. Others believe the answer lies in genetic modification, designing humans who can survive conditions that would kill any person alive today. Both paths raise questions that go far beyond engineering. But before any of that, you have to understand what actually happens to the body when it spends years drifting through a metal tube far from any planet, because the results of that research are significantly more disturbing than most people expect. Imagine a building with no stairs, no hills, no reason to push against anything. Now, imagine living in that building for 20 years. Your muscles would shrink, your bones would thin, your heart, never asked to work hard, would quietly reduce its own capacity. Your sense of balance, calibrated over a lifetime of gravity, would eventually stop making sense entirely. This is approximately what extended spaceflight does to the human body, and we have only seen the beginning of it in the data we have collected so far. On the International Space Station, crew members exercise 2 hours every day, specifically to fight the deterioration that microgravity causes. They use resistance machines designed to mimic the load that gravity places on muscles and bones. Despite this, they return to Earth measurably weaker. Their legs often cannot support their own weight for days after landing. Their cardiovascular systems need weeks to readjust. 2 hours of daily exercise is also 2 hours that cannot be spent doing anything else on a spacecraft where every minute of crew time matters. Now, stretch that 6-month mission to 10 years. Or 50. The cumulative damage becomes something different entirely. Bone loss sustained over decades, even at a slowed rate with countermeasures, leads to a skeleton that fractures under ordinary strain. Muscle loss that advanced affects not just strength, but organ function. The heart can develop irregular rhythms. Fluid that normally pools in the legs redistributes toward the head in microgravity, increasing pressure inside the skull and against the eyes. Long term, this causes structural changes to the optic nerve and can permanently impair vision. Several astronauts have returned from longer missions with vision that did not fully recover. Cosmic radiation compounds every one of these problems, high-energy particles passing through the body-damaged DNA. The body has repair mechanisms, but they are not perfect. Over years of exposure, errors accumulate. Some become cancerous, others affect the nervous system. Research on mice exposed to simulated cosmic radiation showed significant cognitive decline, including memory impairment and reduced ability to problem solve. These are not minor effects. A crew experiencing cognitive degradation mid-mission faces a danger that no extra equipment can fix. The immune system also behaves strangely in space. Some functions become overactive, causing inflammation. Others become suppressed, leaving the crew vulnerable to infections that a healthy immune system on Earth would handle without effort. Latent viruses that the body normally keeps dormant, including members of the herpes family, have been shown to reactivate in astronauts during spaceflight. What all of this means is that the crew of any long interstellar mission is not just a team of explorers. They are a collection of biological systems slowly being degraded by an environment they were never meant to enter, unless the ship itself is designed to fight back. And designing that ship turns out to be one of the most ambitious engineering challenges ever attempted. If you cannot slow the journey down and you cannot put the crew to sleep indefinitely, there is one remaining option. You accept that the journey will take longer than a human life, and you build a ship designed for multiple generations to live and die inside it. A generation ship. The people who leave Earth would not arrive at the destination. Their children would not arrive. Depending on the speed of travel, it might be their grandchildren or great-grandchildren or descendants many generations removed who finally see the destination for the first time. The concept is not new. Science fiction has explored it for decades. But researchers and engineers have started to take it seriously as a genuine long-term option, because it sidesteps several of the hardest biological problems by simply accepting that this is a multi-generational project. The engineering requirements are staggering. First, size. A generation ship cannot be a cramped capsule. It has to function as a self-contained civilization. Living quarters, medical facilities, agricultural systems, schools, spaces for recreation and social life. Estimates for the minimum viable population to avoid genetic bottlenecking. The narrowing of a gene pool to dangerously low diversity range from a few hundred to several thousand people. Some models suggest you need at least 10,000 people to maintain a genetically healthy population over multiple centuries of isolation. 10,000 people require a ship of extraordinary scale. Second, food. Every calorie consumed on the journey has to be produced on board. Hydroponics, carefully managed soil ecosystems, and possibly lab-grown protein are the leading candidates. The system has to be resilient enough that a single crop failure does not become a famine. It has to run continuously for centuries without resupply. Third, air and water. These must be cycled endlessly through closed-loop systems with near-perfect efficiency. A small leak in a water recycling system on Earth is a maintenance problem. On a generation ship, it could be a crisis. Fourth, and perhaps most underestimated, social structure. You cannot draft a constitution for people who will be born 200 years into the voyage. The ship needs governance systems stable enough to persist across generations, without the external pressures that keep societies in check on Earth. No other nations, no outside trade, no immigration, just the people already on board and their descendants. History suggests that isolated, closed societies develop in unexpected ways. Some thrive, some fracture, some produce the kind of rigid hierarchy that makes the original mission impossible to sustain. A generation ship is not just an engineering project. It is a social experiment conducted at the scale of centuries, with no option to quit. And all of this assumes the crew wants to go. The harder question is what happens to the generations who never chose to be there at all. Isolation is not just uncomfortable, it is physiologically destructive. In the 1950s, researcher John Lilly suspended human subjects in sensory deprivation tanks to study the effects of removing outside stimulation from the mind. Subjects began experiencing hallucinations within hours. Their sense of identity became unstable. Some reported terrifying visions. Others described a profound sense of dissolution, as if the boundary between self and environment had dissolved. That was hours. Extended isolation, measured in weeks and months, produces effects that go beyond hallucinations. Studies of prisoners held in solitary confinement show measurable changes in brain structure. The hippocampus, the region involved in memory and spatial navigation, appears to shrink. Anxiety disorders emerge. Depression deepens. In some cases, cognitive function declines in ways that do not fully reverse even after isolation ends. Now consider the specific isolation of deep space. It is not just that you are away from other people outside your crew. It is the totality of the disconnection. No night sky you recognize, no seasons, no cities, no wilderness, no other living thing beyond the walls of the ship. The same corridors, the same faces, the same sounds, day after day, year after year. And as the ship moves further from Earth, communication delays grow. At the distance of 1 light year, a message to Earth takes 1 year to arrive. A reply takes another year to return. Any exchange of information has a minimum round-trip delay of 2 years. Researchers who study Antarctic winter over cruise, teams that spend months in extreme isolation at research stations, have documented a phenomenon sometimes called the third quarter phenomenon. Roughly 3/4 of the way through an isolation period, psychological stress peaks, irritability rises, cognitive performance declines, interpersonal conflict escalates. These crews know they are going home. They have a fixed end date. They are still on the same planet. An interstellar crew would have none of those anchors. NASA has invested heavily in studying group dynamics for long-duration missions. They have run simulations, isolated research crews in Mars, analog environments for up to a year, and studied the results carefully. What they consistently find is that the social dynamics inside a small, confined group under stress are fragile in ways that are difficult to predict and nearly impossible to fully design around. Trust breaks down, hierarchies become contested, small irritations compound into serious conflicts. On a generation ship, there is nowhere to go, no airlock to step out of, no base to transfer to. Whatever psychological system you design into the ship at launch has to hold for centuries. That is not a psychology problem. That is something closer to a miracle. And yet, even if you solved all of it, even if every crew member were psychologically resilient and the social structure held perfectly, you still have to feed them for hundreds of years without a single resupply. Every breath you take on Earth is part of a system that has been running for billions of years. Plants absorb carbon dioxide and release oxygen. Animals absorb oxygen and release carbon dioxide. Bacteria break down waste into nutrients. Water evaporates, condenses, and falls again. Everything is connected in loops so old and so stable that we have never had to think about maintaining them. On a generation ship, you have to build every single one of those loops from scratch, in a metal structure moving through a vacuum, with no outside input and no room for failure. Start with air. The human body consumes roughly 0.5 kilogram of oxygen per day. A crew of 1,000 people requires 500 kilograms of oxygen daily. On Earth, you simply breathe. On a spacecraft, oxygen has to be generated, usually through a process called electrolysis, splitting water molecules into hydrogen and oxygen using electricity. The system has to run continuously, and the byproduct hydrogen has to be safely managed. Carbon dioxide has to be captured and removed before it reaches toxic concentrations. The International Space Station uses a carbon dioxide removal assembly that requires regular maintenance and periodic replacement of chemical canisters. Scaling that system for a crew of thousands over centuries requires technology significantly more robust than anything currently deployed. Water is equally critical and equally complicated. Humans need roughly 2 liters of drinking water per day, plus more for cooking and hygiene. On the International Space Station, water is recycled with roughly 90% efficiency, including from urine. The remaining 10% has to be resupplied. There is no resupply on an interstellar mission. Water recycling efficiency has to approach 100%, sustained for centuries. A drop in efficiency compounds into a crisis. Food is the most complex challenge of all. Plants grown hydroponically can produce calories, but not the full nutritional spectrum humans need. Soil-based systems produce more variety but require enormous volume and careful biological management. Insects are highly efficient protein sources and are being studied seriously as part of long-duration mission food systems. Lab-grown meat, still in its early commercial stages on Earth, could provide protein without the resource demands of raising animals, but the technology would have to be manufactured on board, maintained for centuries, and operated by people with varying levels of relevant expertise. A single crop pathogen, a fungus or bacteria that spreads through a hydroponic bay could devastate food production before anyone realizes what is happening. Redundancy is the only answer to most of these problems. Multiple independent food systems, multiple water recycling chains, multiple air management systems, each capable of running the ship alone if the others fail. Redundancy means mass. Mass means more fuel to accelerate and more fuel to stop. Everything in spacecraft design pulls against everything else, and all of it assumes the ship holds together across the centuries of the journey. Which brings us to the single most underappreciated problem of interstellar travel. Nothing we have ever built was designed to last 1,000 years without access to a repair shop. The oldest functioning mechanical clock in the world was built in the 1300s. It has been continuously maintained, repaired, and partially rebuilt by generations of skilled craftspeople for over 600 years. Without that constant human intervention, it would have stopped long ago. Now ask yourself, what machine built by humans has ever run for 1,000 years without maintenance? The answer is none, not one. A generation ship is not just a vessel. It is a civilization-sustaining machine that has to keep operating across centuries through conditions its designers cannot fully anticipate, maintained by people who may have never set foot on Earth and may not fully understand the systems they are keeping alive. The engineering challenge is unlike anything in human history. Consider the materials alone. Metal fatigue is real. Every metal component under repeated stress develops microscopic cracks over time. On Earth, we inspect structures regularly and replace components before they fail. On an interstellar ship, you cannot import replacement parts. Every spare has to be on board from the start, or manufactured from raw materials using systems that are themselves subject to wear. Three-dimensional printing and advanced manufacturing technology offer a partial solution. If you carry the raw materials and the machines to shape them, you can theoretically fabricate replacement parts for many systems. But the manufacturing machines themselves will break down, and the machines that fix those machines will break down. At some point, the chain of maintenance reaches a limit. Electronics are particularly vulnerable. Cosmic radiation damages semiconductor components over time. The computers managing life support, navigation, and medical systems cannot be the same hardware that launched. They have to be rebuilt, upgraded, and replaced by people with the knowledge and materials to do so. Software is its own dimension of risk. A generation ship launched today would carry software designed by people with the assumptions, priorities, and blind spots of today. A century from now, that software may be running on hardware it was never designed for, maintained by people who no longer fully understand its architecture, managing problems its original designers never imagined. The history of software on Earth is full of critical failures caused by edge cases nobody anticipated. On a generation ship, an edge case that crashes a navigation system or corrupts a life support algorithm is not an inconvenience. It is catastrophic. Some researchers argue that the solution is radical simplicity. Design every critical system with the fewest possible moving parts, the most understandable possible logic, and the deepest possible redundancy. Build for a crew that might not have specialist engineers, only generalists who understand enough to keep things running. Others argue the opposite, that the complexity is unavoidable, and the answer is artificial intelligence sophisticated enough to self-diagnose, self-repair, and adapt over centuries without human guidance. Both approaches carry their own profound risks, but here is what makes all of this worth considering, despite the difficulty. Humans have a record of solving problems that once seemed impossible, and some of the propulsion ideas currently on the drawing board suggest the journey to 1 light year might not need to take centuries at all. The physics gets stranger from here, and stranger, in this case, means faster. In the late 1950s, a group of serious physicists sat down and asked a question that most people at the time would have called insane. What if you propelled a spacecraft by detonating nuclear bombs behind it? Not as a joke, not as science fiction, as a genuine engineering proposal. The project was called Orion. It was funded by the United States government, developed by some of the brightest minds in physics, and it worked on paper in ways that still command respect today. The basic concept was straightforward. A spacecraft carries thousands of small nuclear devices. One by one, they are released behind the ship and detonated. A thick metal plate at the rear of the spacecraft, called a pusher plate, absorbs the blast and transfers the energy forward as thrust. Shock absorbers between the plate and the crew compartment smooth out the impulse. Each detonation pushes the ship. Thousands of detonations, spaced precisely, produce sustained acceleration. The numbers are genuinely remarkable. Theoretical designs suggested an Orion-style spacecraft could reach speeds of 3 to 5% of light speed. At 3% of light speed, 1 light year would take roughly 33 years. At 5%, about 20 years. 20 years to cross 1 light year. That is within the range of a single human lifetime. The project was eventually cancelled, partly due to the 1963 Partial Nuclear Test Ban Treaty, which prohibited nuclear detonations in space. But the physics was never disproved. The concept was not abandoned because it failed. It was abandoned because of politics and treaty obligations. Modern variations on the concept have refined the idea significantly. Project Daedalus, designed by the British Interplanetary Society in the 1970s, proposed using nuclear fusion micro-explosions rather than fission bombs. Tiny pellets of deuterium and helium-3 would be compressed and ignited by electron beams, producing bursts of plasma that drive the ship forward. Project Daedalus design suggested speeds approaching 12% of light speed. At that velocity, 1 light year takes less than 9 years. The engineering barriers are enormous. Helium-3, one of the proposed fuels, is extraordinarily rare on Earth, though it exists in larger quantities on the Moon and in the atmospheres of the outer planets. The ignition systems required operate at tolerances that push the edge of what materials science can currently achieve. But the physics is real. The trajectory from concept to engineering is clear, even if the distance along that trajectory is vast. Nuclear pulse propulsion represents the most credible pathway to interstellar speeds that does not require physics we have not yet discovered, and it is not even the fastest idea on the table, because some researchers have been working on an engine that does not burn anything at all. Every star in the sky is a fusion reactor. Hydrogen atoms compressed by gravity to extraordinary densities fuse together, releasing energy at a scale that makes every other energy source humanity has ever used look trivial. Our star alone releases the equivalent of roughly 400 trillion watts every second. For decades, physicists have been trying to recreate that process in a controlled environment on Earth. The appeal is obvious. Fusion fuel, primarily hydrogen isotopes found in seawater, is effectively unlimited. The energy output dwarfs fission. The waste products are far less dangerous than those of conventional nuclear reactors. Progress has been slow. The famous joke in fusion research is that practical fusion power has been 20 years away for the past 60 years. But recent developments have shifted the tone of that conversation. In December 2022, the National Ignition Facility in California achieved ignition for the first time. A fusion reaction that produced more energy than the lasers used to start it. It was a narrow margin, and the overall system still consumed far more energy than the reaction released. But it was a threshold crossed. For spacecraft propulsion, fusion offers something beyond just energy density. It offers directional thrust. A fusion rocket would not simply heat a propellant the way chemical rockets do. It would use the plasma produced by fusion reactions directly as exhaust, channeled and accelerated by magnetic fields. The exhaust velocity of a fusion drive would be orders of magnitude higher than any chemical rocket, meaning far more thrust from far less mass. Theoretical fusion rocket designs suggest specific impulses, the measure of fuel efficiency in rocketry, roughly 1,000 times greater than the best chemical rockets currently in operation. That difference in efficiency changes the entire calculation of what a spacecraft can carry, how fast it can accelerate, and how far it can travel. At the performance levels theoretical fusion drives could achieve, speeds of 10 to 20% of light speed become plausible over long acceleration periods. 1 light year at 10% of light speed takes 10 years. The practical barriers are significant. Sustaining a fusion reaction hot enough and dense enough to produce useful thrust requires magnetic confinement systems of extraordinary precision. The materials that make up the engine must withstand temperatures that exceed anything in our current engineering experience. Private companies, including TAE Technologies, Helion Energy, and Commonwealth Fusion Systems, are all pursuing fusion power with timelines measured in years rather than decades. If any of them succeed in producing practical fusion energy on Earth, the pathway to fusion propulsion opens significantly. The connection between Earth-based energy and interstellar propulsion is direct. Solve fusion here, and you have taken the most important step towards solving it in space. But there is an approach to interstellar propulsion that requires no onboard fuel at all, no reactor, no combustion, just light. And it might be the fastest thing we can actually build. Light has no mass, but it does have momentum. This is not intuitive. We do not feel sunlight pushing us when we step outside, but the pressure is real, measured precisely, and at the right scale, it becomes a viable propulsion mechanism. A solar sail works by catching photons the way a boat sail catches wind. As photons reflect off a large, thin surface, they transfer a tiny amount of momentum to it. Individually, each photon contributes almost nothing, but across a sail the size of a city block, receiving billions of photons per second from a powerful light source, the cumulative push adds up. Japan's Ikaros spacecraft demonstrated solar sailing in deep space in 2010, becoming the first vehicle to successfully use photon pressure for interplanetary propulsion. It was a proof of concept, and it worked. But solar sails powered by sunlight alone are slow. The pressure of sunlight decreases with distance from our star, and even near Earth it produces only modest acceleration. The leap forward comes from replacing sunlight with a directed laser beam. A laser sail, sometimes called a light sail or photon drive, would be pushed by a laser array based in space or on the ground, beaming focused light onto a reflective sail attached to a tiny spacecraft. The laser does not need to travel with the ship. It stays behind and pushes from a distance. This is the core idea behind Breakthrough Starshot, a research initiative announced in 2016 with backing from physicist Stephen Hawking and investor Yuri Milner. The proposal involves building a laser array capable of delivering 100 gigawatts of focused light onto a sail roughly a few meters across, attached to a spacecraft the size of a postage stamp. The acceleration would be extraordinary. In theory, the tiny spacecraft could reach 20% of light speed within minutes of the laser firing. At 20% of light speed, 1 light year takes 5 years. The challenges are significant, but they are engineering challenges rather than physics barriers. The laser array required would be unlike anything ever built, likely requiring thousands of smaller lasers firing in perfect coordination. The sail material has to reflect the laser efficiently without being destroyed by it. At 20% of light speed, even the thin gas and dust of interstellar space becomes a sandblasting hazard. Pointing the laser accurately enough to stay on the sail as the spacecraft accelerates away is a precision problem that has no current solution, only promising approaches. And the spacecraft itself, at postage stamp scale, cannot carry a human. It cannot carry much of anything beyond basic sensors and a communication system. But it could carry a camera. It could carry instruments. It could send back data from 1 light year out. or from the nearest star system. Years before any crewed mission would be possible, the first interstellar travelers may not be human at all, and the project designed to send them is already underway. In April 2016, a press conference in New York City announced something that would have sounded like science fiction just a decade earlier: a plan to send spacecraft to another star within a generation. Breakthrough Starshot, funded with $100 million in initial research money, set out to determine whether the laser sail concept was physically achievable. Not in theory, in engineering reality. The target was Alpha Centauri, the nearest star system, 4.2 light-years away. The goal was to send a fleet of gram-scale spacecraft, called starships, accelerated by a ground-based laser array to 20% of light speed. At that velocity, the journey would take roughly 20 years. Data would begin arriving back on Earth about 4 years after that, given the travel time of the signal. The proposal broke the problem into components and asked which ones were solvable with technology either available today or foreseeable within the coming decades. The laser array is the hardest part. 100 gigawatts of focused power requires either a single extraordinary laser or, more practically, a phased array of roughly 100 million small lasers synchronized to fire as a single coherent beam. The technology for individual laser units already exists. The synchronization at that scale does not, but researchers believe it is achievable. The starship itself has to be extraordinarily light. Current prototype designs propose a total mass of around 1 gram, integrating a camera, communication system, power source, and navigation capability into a wafer roughly the size of a postage stamp. Advances in miniaturization, particularly in microelectronics and photonics, have made this increasingly plausible. The sail material is another active area of research. It has to be highly reflective to maximize the push from the laser. It has to be extraordinarily thin to keep mass low. And it has to withstand both the intense laser energy during acceleration and the particle impacts of interstellar travel at high velocity. Progress has been steady. Researchers have tested candidate sail materials in the laboratory. Engineering papers have worked through the synchronization challenges for large phased laser arrays. The physics group at UC Santa Barbara has produced detailed technical analyses of each subsystem. A full-scale demonstration is still years away. The complete system, laser array, sail, and starship combined, would require an infrastructure investment comparable to large scientific facilities like particle accelerators. Estimates for the full project cost range into the billions of dollars. But Breakthrough Starshot has done something valuable beyond the technical work. It has moved interstellar travel from the category of distant speculation into the category of serious engineering planning. Scientists are now writing peer-reviewed papers about sail materials and laser tolerances, not about whether the idea is worth pursuing. That shift matters. Because even a probe, even a gram-scale camera with no crew, crossing 1 light-year and sending back data, would represent something that has never happened in human history. The first confirmed look at interstellar space from inside it. And that first look would change everything we think we know about what is out there. 1% of the speed of light. It sounds modest. After all, 99% of light speed remains out of reach. 1% feels like barely getting started. But 1% of light speed is 6,700,000 miles per hour. Let that settle for a moment. The fastest military jet ever built, the SR-71 Blackbird, topped out at about 2,200 miles per hour. 1% of light speed is roughly 3,000 times faster than that. At 1% of light speed, you would cross the entire United States in about 2 seconds. You would circle Earth in roughly 20 seconds. You would reach the Moon in about 3.5 minutes. And you would cross 1 light year in 100 years. 100 years is a long time. It is longer than a human life, but it is not an incomprehensible span of civilization. 100 years ago from today, cars were becoming common. The first commercial radio broadcasts had just begun, and the first transatlantic flight was only a few years in the past. The pace of change in 100 years is enormous. More importantly, 1% of light speed is a speed that serious propulsion concepts can actually target. Nuclear pulse propulsion designs suggest it is achievable. Advanced fusion drives point toward it. Even highly optimized ion drives, given enough time to accelerate, could theoretically approach it. It is not a fantasy number. It is an engineering target. Now, push to 5% of light speed. 1 light year in 20 years. A manageable mission duration. Crew members who leave in their 30s could arrive in their 50s, still capable of conducting research and establishing whatever foothold is possible. 10% of light speed gives you a 10-year crossing, the duration of a demanding but survivable career assignment. 20%, the Breakthrough Starshot target for its tiny probes, brings it down to 5 years. Each percentage point of light speed gained is not just a faster journey, it is a fundamentally different relationship with interstellar space. It is the difference between a mission that spans generations and one that fits inside a human life. The gap between our current best speed and 1% of light speed is large, but it is not arbitrary. There is a direct line from current propulsion research to that target, even if the line passes through decades of engineering work. And once you start approaching even a small fraction of light speed, something else begins to happen. Something that Einstein predicted over 100 years ago, and that no experiment has ever contradicted. Time itself begins to behave differently. And the implications of that are stranger than almost anything else in this entire journey. Time is not fixed. This is one of the most verified and least intuitively understood facts in all of physics. Einstein's theory of special relativity, published in 1905, showed mathematically that time passes at different rates depending on how fast you are moving relative to something else. The faster you move, the slower time passes for you compared to someone who is stationary. This is not a metaphor. It is not a philosophical concept. It is a measurable physical reality that affects every object in the universe, including the clocks in the GPS satellites orbiting Earth right now, which have to be corrected daily to account for relativistic time differences or navigation errors would accumulate rapidly. At the speeds humans travel today, the effect is too small to notice without precise instruments. But as you approach a significant fraction of light speed, the effect becomes dramatic. At 10% of light speed, time dilation is modest. A journey that takes 10 years by Earth's clock would feel like about 9 years and 11 months to the crew, barely noticeable. At 50% of light speed, the effect sharpens. A journey of 10 Earth years would feel like about 8.5 years to the crew. At 90% of light speed, a 10-year journey by Earth's measure feels like about 4.5 years to the traveller. At 99% of light speed, a 10-year Earth journey compresses to about 1.5 years of experienced time for the crew. At 99.9% of light speed, 10 Earth years pass in roughly 5.5 months of crew time. The closer you get to light speed, the more extreme the compression. In principle, a crew travelling at near light speed could cross the entire observable universe in a single human lifetime, while billions of years pass on Earth. For a 1 light-year journey at moderate relativistic speeds, the practical impact is limited. At 10 or 20% of light speed, the time difference between crew time and Earth time is real, but not dramatic. But the concept matters for a deeper reason. It means that the universe does not strictly forbid humans from reaching the stars within a human lifetime. It forbids us from doing it while keeping time synchronized with the people we leave behind. You can cross a light year in less time than it takes by Earth's clock, but when you arrive, more time will have passed at home than you experienced on the ship. The people who waved goodbye age faster than you do, and nowhere is that made more vivid than in one of the most famous thought experiments in the history of physics. 2 identical twins stand on a launch pad, One boards a spacecraft, the other stays on Earth. The traveler launches, accelerates to a significant fraction of light speed, travels outward for some years, turns around, and returns. When the ship lands, the twins stand face to face again. They are no longer the same age. The twin who travelled is younger, not slightly younger, depending on the speed and duration of the journey, significantly younger. The traveller experienced fewer years. Time passed more slowly for them, while they moved at high velocity. This is the twin paradox. It earns that name because the outcome feels impossible. How can the same amount of time have passed differently for two people who started together and ended together? The resolution lies in the fact that the travelling twin did something the stationary twin did not. They accelerated. They changed direction. They decelerated. These changes break the symmetry between the two observers and produce a genuine, measurable difference in elapsed time. The twin paradox is not theoretical. We have confirmed the underlying physics repeatedly. In 1971, physicists flew extremely precise atomic clocks around the world on commercial jets and compared them to identical clocks that stayed on the ground. The airborne clocks, moving faster and at higher altitude, showed measurable time differences consistent with relativity. The clocks that flew were slightly behind the clocks that stayed home. Particle accelerators confirm it constantly. Unstable particles moving at near light speed inside accelerators decay more slowly than identical particles at rest, exactly as relativity predicts. Their internal clocks, in a sense, run slower. For a mission to 1 light-year, the practical implication is this. A crew travelling at 10% of light speed would age very slightly less than the 100 years that pass on Earth. At higher speeds, the gap grows. If humanity ever achieves travel at a substantial fraction of light speed, the crews who make those journeys will return younger than their contemporaries. They will return to a world that has moved forward without them. People they knew will be gone. Technology will have changed. The world that sent them may look very different from the one that receives them. There is something profoundly isolating about that prospect, beyond the isolation of the journey itself. You do not just leave Earth behind, you leave its timeline. But before any of that becomes relevant, the travellers would experience something else entirely during the journey. Something that turns the familiar image of a starfield into something almost unrecognizable. At high fractions of light speed, the universe looks nothing like it does from the ground. Stand outside on a clear night and look up. Stars scattered across the dark, roughly evenly distributed in every direction, each one a point of steady light. Now, imagine accelerating to 50% of light speed and looking again. Everything has changed. At high velocities, a phenomenon called relativistic aberration compresses the apparent positions of stars toward the direction of travel. Stars that were spread evenly across your field of view bunch together ahead of you, as though the universe is crowding forward into your path. The stars behind you spread apart and dim. The forward hemisphere fills with light, while the rear hemisphere darkens. At 90% of light speed, nearly all visible stars have compressed into a bright ring directly ahead of the ship, a halo of blue shifted light surrounding a central dark region. The color shift is dramatic. Light from stars ahead of you gets compressed in wavelength, pushing toward the blue and ultraviolet end of the spectrum. Stars behind you shift toward the red and infrared, eventually dropping out of visible range entirely. The sky ahead glows bluish-white. The sky behind fades to near black. This is not an optical illusion or a camera effect. It is what physics actually produces for an observer moving at those speeds. At near light speed, the central dark region ahead fills with radiation of an entirely different kind. The cosmic microwave background, the faint echo of the early universe that fills all of space at microwave frequencies, gets blue shifted into dangerous gamma radiation directly ahead of the ship. Without shielding, this forward radiation would be lethal. The crew would not be looking out a window. in any traditional sense. Cameras tuned to the visible spectrum would show a distorted, shifting picture. Instruments covering a broader range of frequencies would be essential for navigation. Navigation itself becomes a challenge. Star positions appear different from their actual positions due to aberration. The constellations we use as reference points on Earth are unrecognizable at high speed. A ship needs precise computer modeling to translate what instruments observe into an accurate map of actual stellar positions. Even time contributes to the strangeness. As the ship approaches 1 light year at high speed, the light arriving from ahead has been traveling for a year. The crew is effectively looking at the past of the region they are approaching. The universe at near light speed is not the universe of astronomy textbooks. It is shifted, compressed, recolored, and radiatively hostile, beautiful in a way that belongs to a category beyond normal beauty, and lethal in a way that adds yet another layer to an already staggering list of dangers. Because even before you consider what happens to the crew, you have to consider what happens to the ship itself. At these speeds, space is not empty, and anything in the way becomes a weapon. Space is not empty. Between the stars, the interstellar medium contains gas, mostly hydrogen and helium and dust, microscopic grains of silicate, carbon, and ice, some smaller than a bacterium, drifting through the dark. At normal human speeds, these particles are irrelevant. Voyager 1 has been traveling through interstellar space for years, and the dust presents no meaningful hazard at its velocity. But at 10% of light speed, a grain of interstellar dust, the size of a grain of sand, carries kinetic energy equivalent to a rifle bullet. At 20% of light speed, that same grain hits with the energy of a small explosive charge. A spacecraft moving at those velocities is not gliding through empty space. It is running into a continuous stream of microscopic projectiles, each carrying destructive energy far beyond what its size suggests. The numbers are difficult to feel without context. Kinetic energy scales with the square of velocity. Double the speed, quadruple the energy. At relativistic speeds, the relationship becomes even more extreme. A particle that would bounce harmlessly off a spacecraft at low speed becomes a penetrating round at 10% of light speed. Over a journey of 1 light year, the cumulative damage from interstellar dust impacts would be severe without protection. Hull material erodes, sensitive instruments are destroyed, optical surfaces become pitted and opaque. Engineers have proposed several approaches to the problem. The first is shielding. A thick layer of material at the nose of the spacecraft absorbs and deflects impacts. Beryllium, graphite composites, and aerogel have all been proposed as candidate materials. The shielding adds mass, which requires more energy to accelerate. The second is a magnetic deflector. If the spacecraft generates a strong enough magnetic field ahead of it, charged particles in the interstellar medium can be deflected around the hull without physical contact. Neutral dust grains, however, are not affected by magnetic fields. A magnetic shield handles the gas, but not the solid particles. The third approach, proposed specifically for the Breakthrough Starshot probes, is geometry. Make the spacecraft so thin and so edge-on to the direction of travel that the cross-section presented to incoming particles is minimized. A flat sail and a thin chip, oriented carefully, would intercept far fewer particles than a conventional cylindrical spacecraft. Each solution is partial. The full answer likely involves combining all three approaches. There is a final problem that no physical shield addresses. The farther from Earth the spacecraft travels, the longer any communication delay grows. At 1 light year out, even a signal asking for help takes 1 year each way. And that communication breakdown creates its own category of danger, one that affects not just the spacecraft, but everything the crew needs to know about the world they left behind. Voyager 1 is about 15 billion miles from Earth. A radio signal from its transmitter, traveling at the speed of light, takes over 22 hours to reach us. When mission controllers send a command to Voyager, they wait nearly 2 days for any response. Every interaction is a long, slow exchange of messages across an enormous gulf. Now scale that to 1 light year. A signal sent from a spacecraft at 1 light year distance takes 1 year to arrive on Earth. A reply takes another year to return. Any exchange of information has a minimum round-trip delay of 2 years. This is not a technology problem. No antenna, no matter how powerful, can make information travel faster than light. The delay is baked into physics itself. For a crewed mission, the implications are profound. Medical emergencies cannot be managed in real time by doctors on Earth. Engineering crises cannot be diagnosed with expert help from mission control. Navigation decisions cannot be confirmed before they are executed. Every choice the crew makes is made alone, with information that is already at least 1 year old. The psychological weight of this cannot be overstated. Humans are social creatures. We evolved in tight communities where information about threats, resources, and relationships was exchanged continuously. The crew of an interstellar mission would exist in a state of total informational isolation from the civilization that sent them. News from Earth would arrive in batches, already a year out of date. Events that felt immediate and urgent when transmitted would arrive after their outcomes were already decided. People they care about could become ill and recover, or not recover, in the time between sending a message and receiving a reply. The relationship between an interstellar crew and Earth would be nothing like any human relationship that has ever existed. It would be closer to reading letters from a distant relative, letters that take a year to arrive and describe a world that has already moved on. For a generation ship, the communication problem eventually becomes irrelevant in a different way. Generations born on the ship may have no living connection to Earth at all. Earth becomes, for them, a story, a place of origin, in the same way that most people today relate to the villages their great-grandparents came from. The farther you go, the more the crew is on their own, not just physically, informationally, culturally, emotionally. Unless the ship carries something capable of making decisions without human input, something that does not need to radio Earth for guidance, something that can think for itself across the centuries. The role of artificial intelligence in interstellar travel is not a side note. It may be the single most important factor in whether any of this is possible at all. A spacecraft 1 light year from Earth faces a simple truth: no one is coming to help. Every system failure, every medical emergency, every navigation correction, every conflict between crew members, every unexpected phenomenon encountered in interstellar space has to be handled by whatever and whoever is on board. For a crewed mission, this places extraordinary demands on the crew themselves. They need to be generalists of the highest order, capable of performing surgery, repairing advanced electronics, managing psychological crises, and making engineering decisions that would ordinarily require teams of specialists. Artificial intelligence changes this equation fundamentally. An advanced AI system on an interstellar spacecraft could serve as physician, diagnosing conditions and guiding treatment using comprehensive medical databases and real-time sensor data. It could serve as engineer, continuously monitoring thousands of systems and identifying failures before they become catastrophic. It could serve as navigator, processing instrument data and making course corrections with precision no human crew could match. It could also serve as historian, archivist, and teacher, preserving the accumulated knowledge of Earth's civilization and transmitting it to generations born on the ship who have never lived anywhere else. For an uncrewed mission, like the Breakthrough Starshot probes, AI is not optional, it is the mission. A postage-stamp spacecraft with no crew has to make all navigation and operational decisions autonomously. At 20% of light speed, signals from Earth take years to arrive. Real-time control is impossible. The AI on such a probe has to be capable of identifying its target, conducting whatever observations are possible during its brief encounter, prioritizing which data to transmit in the limited window available, and managing any unexpected events without any possibility of human consultation. Current artificial intelligence systems are powerful but narrow. They excel at specific tasks they have been trained for and fail in unpredictable ways at tasks outside that training. An interstellar AI needs something closer to general intelligence, the ability to reason across unfamiliar domains and handle situations its designers never anticipated. That capability does not yet exist in any deployed system. The trajectory of AI development suggests it may exist well before any interstellar mission is launched. But the reliability requirements for a system that has to function without maintenance or update for decades or centuries are beyond anything currently tested. There is also a question that gets less attention than it deserves. If an AI system manages a generation ship across centuries, developing and adapting as it goes, what is its relationship to the crew? Is it a tool, a colleague, something for which we do not yet have a word? The ethical dimensions of interstellar AI are as complex as the technical ones. But all of these questions, the engineering, the biology, the physics, the psychology, the AI, ultimately point toward a single destination, 1 light-year away. And what is actually there turns out to be more interesting than most people expect. 1 light-year is a specific distance. It is not halfway to Alpha Centauri. It is not a named star or a catalogued object. It is simply a distance, a marker on the road from here to there. But it is not empty. The region between roughly 1,000 astronomical units and roughly 100,000 astronomical units from our star, where 1 astronomical unit is the distance from Earth to our star, is believed to contain a vast and largely unmapped structure called the Oort Cloud. 1 astronomical unit is about 93 million miles. 1,000 astronomical units is where the influence of our star's solar wind begins to give way to interstellar space. 100,000 astronomical units is roughly 1.6 light-years. 1 light-year sits deep within the outer Oort Cloud. The Oort Cloud is theoretical in the sense that no spacecraft has yet reached it, and no telescope has directly imaged individual objects within it. But it is extremely well supported by the behavior of long-period comets, those that arrive in the inner solar system from trajectories suggesting origins in the far outer reaches. Their paths, traced backward, point to a vast spherical shell of icy bodies surrounding our star at enormous distance. At 1 light-year, a spacecraft would be surrounded by a population of objects unlike anything in the familiar solar system. Comets in the Oort Cloud are not yet comets in the conventional sense. They are dormant, frozen bodies that only develop their characteristic tails when gravitational disturbances send them falling toward the inner solar system, where our star's heat vaporizes their ices. These objects range in size from small boulders to bodies potentially hundreds of miles across. They contain water, ice, carbon dioxide, methane, ammonia, and complex organic molecules. Some researchers believe they may represent the most pristine material in the solar system, unaltered since the formation of the planets 4.5 billion years ago. A mission that reached 1 light-year would be the first direct investigation of the Oort Cloud. It would answer questions about the composition of the early solar system that cannot be answered any other way. It would map, for the first time, the actual boundary between our star's domain and interstellar space. It would also provide the first in situ measurements of the true interstellar medium, the gas and dust between the stars, at a location no instrument has ever sampled. The science alone would justify the mission, independent of any question about what lies beyond. And 1 light-year out, looking back, the view of home would be something no human has ever seen. Our star reduced to a bright point, Earth invisible. The solar system compressed into a single gleam of light against the dark. That view would do something to the people who saw it, something that goes beyond science. And it leads directly to the question of what this journey means for us as a species. 4.5 billion years ago, a cloud of gas and dust collapsed under its own gravity and began to form what we now call the solar system. The inner regions became dense and hot. Dust and gas clumped into rock. Rock accumulated into planets. The 4 inner planets formed solid surfaces. The 4 outer giants gathered enormous envelopes of gas and ice. But not all of the material ended up in planets. Vast amounts of icy debris were flung outward by the gravity of the forming giant planets, scattered to the far edges of the system. Over billions of years, this debris settled into a roughly spherical cloud extending from around 2,000 astronomical units out to 100,000 astronomical units or beyond. This is the Oort Cloud, a ghostly shell of frozen leftovers from the birth of our solar system, surrounding everything we know at a distance so great that light takes over a year to cross it. The total number of objects in the Oort Cloud is unknown. Estimates range from hundreds of billions to over 1 trillion individual bodies. Most are small, some are large, and virtually none have been directly observed. We infer the Oort Cloud's existence from comets, long-period comets, those that take hundreds or thousands of years to complete a single orbit, arrive from directions spread evenly across the sky, rather than clustered near the plane of the solar system like short-period comets. This distribution strongly suggests they originate from a spherical structure rather than a flat disk. Their extremely elongated orbits trace back to origins deep in the outer cloud. What sends them falling inward is gravitational perturbation. A passing star, a giant molecular cloud, or the tidal force of the galaxy itself occasionally disturbs the orbital stability of Oort Cloud objects, nudging some of them onto paths that carry them falling toward the inner solar system over millions of years. The first comet to reach the inner solar system from the Oort Cloud on its current orbit began that fall long before humans existed. At 1 light-year distance, a spacecraft would be moving through a region populated by these ancient, frozen travelers before they begin their long inward plunge. The scientific value is extraordinary. Oort Cloud objects have been in deep freeze since the formation of the solar system. Their chemistry is a direct record of the material that existed in the early solar system before any planetary processing altered it. Studying them directly is studying the raw ingredients of everything in our neighborhood of space, including the ingredients of life. Complex organic molecules have been detected in comets by missions to short-period comets closer to home. The Oort Cloud likely contains far more of them, preserved in pristine cold for billions of years. 1 light-year is not just a distance, it is an archive, and reaching it would mark a moment in human history as significant as any that came before it. Every major expansion of human range has changed what it means to be human. When our ancestors first crossed land bridges between continents, they became a different kind of species, one capable of inhabiting environments they were never biologically designed for. Ice, desert, rainforest, tundra. Each new environment demanded adaptation, innovation, and a willingness to move toward the unknown. When the first Polynesian navigators built canoes and sailed into the open Pacific without maps, using only stars, wave patterns, and the behavior of birds, they crossed distances that most of their contemporaries believed were impassable. They found islands thousands of miles from anything known. When the first long-distance sailing expeditions crossed the Atlantic and mapped the Pacific, they did not just add lines to a chart. They collapsed the psychological boundary between the known and the possible. Each of these expansions looked impossible from the inside of the previous one. Interstellar travel is the next version of this story. The distances are incomparably larger. The timescales are incomparably longer. The engineering barriers are incomparably more difficult. And yet, the underlying dynamic is identical to every expansion that came before. A species at the edge of its known range, looking outward. The pursuit of interstellar travel forces advances in physics, materials, science, medicine, biology, computing, and psychology that have cascading benefits across everything else. Nuclear fusion research aimed at spacecraft propulsion produces energy sources that could power civilization here. Life support systems, designed for century-long missions, produce closed-loop environmental technology applicable to a planet under ecological pressure. Radiation medicine developed for deep space crews advances cancer treatment on Earth. The reach toward 1 light-year is not separate from the problems of this world. It is connected to them at the level of the science that underlies both. There is also something harder to quantify. The knowledge that something exists beyond the boundary you are standing at changes how you relate to where you are. The explorers who first saw the Pacific from the mountains of Panama did not only gain a new ocean, they gained a different understanding of the continent they were standing on. Looking back at Earth from 1 light-year away, the entire solar system visible as a single point of light, everything that has ever happened in human history occurring within that point changes the frame entirely. It is not a shrinking of significance, it is an expansion of context, and with that expanded context comes a question that this entire journey has been building toward, one that does not have a comfortable answer, one that every civilization, if there are others, must eventually face, and the way we answer it will determine everything about what comes next. Here is where we land. 1 light-year is 5,878 billion miles. Our fastest spacecraft would take tens of thousands of years to cross it. Our most ambitious propulsion concepts, if fully realized, could reduce that to somewhere between a decade and a century. The biological, engineering, and psychological barriers are real, serious, and only partially solved. And yet, every single barrier between humanity and interstellar travel is a problem of engineering or biology or physics. Not one of them is a barrier in principle. Not one of them violates a law of nature. Fusion propulsion does not require physics we do not understand. It requires engineering we have not yet built. Radiation shielding does not require new science. It requires materials we have not yet perfected. Closed-loop life support, suspended animation, artificial general intelligence, all of these are hard problems. None of them are impossible ones. The question this journey forces us to ask is not whether it can be done. The question is whether we will still be here as a coherent civilization when the technology to do it matures. That is not a dark thought for its own sake. It is the honest version of the question. Every capability we have discussed, nuclear propulsion, fusion energy, advanced AI, long-duration life support, represents technology that also has other applications. The same fusion engine that could propel a ship to the stars could, if misused, represent an extraordinary concentration of destructive power. The same AI capable of managing a century-long mission autonomously could, in different hands, be applied to very different ends. The civilizations that eventually reach the stars, if the history of exploration on Earth is any guide, are the ones that found a way to direct their most powerful capabilities outward rather than inward. The ones that made it to the next horizon were the ones still capable of building ships when the technology to cross the water finally existed. Interstellar travel is not just a measure of technical capability, it is a measure of civilizational continuity. The 1 light-year mark is close in the sense that the physics is known and the engineering path is visible, even if it is long. It is far in the sense that the journey requires a civilization stable enough, coordinated enough, and ambitious enough to commit to projects measured in generations. Right now, every atom of every person who has ever lived, every city ever built, every piece of music ever composed, every war ever fought, every discovery ever made, fits inside a sphere roughly 8 light hours across, centered on our star. 8 light hours against a universe 93 billion light-years wide. 1 light-year is the first step out of that sphere. Whether we take it is not a question about rockets or physics or fuel. It is a question about us and the answer is still being written.